In this video, we're going to take a look at section 9.1 on testing a claim about two proportions. To test a claim regarding two proportions, we will use the same process that we learned in chapter 8 for testing claims, which is hypothesis testing. So let's review the components of that process. The first step is to identify the claim and write it in mathematical form. The second step is to identify the null and the alternative hypotheses. Then identify alpha and whether the test will be a left tail, right tail, or two-tail test. Then we will calculate the test statistic. Next, determine the critical value and or the p-value in order to draw your conclusion. The initial conclusion will either be to reject or fail to reject the null hypothesis. And then the final conclusion will be in regards to the claim. All right, so that is the same process that we used in chapter 8. It's the same process in chapter 9. The details are going to be different. They are going to be more complex, but the structure of the problem will be exactly the same. And even these extra details only affect certain of these steps. So the claim, the hypotheses, left tail, right tail, two tail, the critical value, the p-value, rejecting or failing to reject, all of that really doesn't change. It's going to be the same as it was in chapter 8. The only thing that really changes here is the test statistic. That becomes a lot more complicated, but the rest of the process really will not change that much. With one exception, which is writing the claim. It's going to involve two proportions instead of one proportion. So instead of having like a proportion be less than or greater than some number, it'll be one proportion being less than or greater than another proportion. So we're going to have two variables in our claim, basically, two population proportions that are going to be referenced. And so that's going to be a little bit different as well. But the idea is still pretty much going to be the same. The requirements for testing claims about a population mean, I did the same thing again. I just did this in the last video. And this is the thing that was supposed to be there in the last video, and it wasn't because I left it as proportion. I'm pretty sure. No, I was on the test statistics screen, but still, same mistake. Copy and paste, and then I forget to change the title, so I apologize for that. So the details here are correct, but the title didn't get changed. Requirements for testing claims about two population proportions. That's what this title should have said. And then this part, of course, isn't even relevant for that. So I apologize for making that mistake again. What I said before, first edition, there's a lot of typos. When you update it, revise it, and release new editions, I'll go back and fix all this. So the requirements for testing claims about two population proportions. There are proportions from two independent simple random samples. For each of the two samples, so we're going to have samples from both of our populations, and they have to be independent of each other. So there can't be any dependencies, any paired data, anything like that. For each of the two samples, the number of successes is at least 5, and the number of failures is at least 5. And as long as those are satisfied, then we can use the process that we're about to use. The test statistic for testing a claim about two proportions, so I made the change that needed to be made here, I just forgot to do it on the last screen, is this monstrosity of a formula. This took me forever just to even get it typed in. So you have to use a special mathematical formatting language called LaTeX, and it was quite a challenge to get all of this typed in using LaTeX. It's a complicated formula. Now remember, p-hat means sample proportion, but we have two samples, so we have to distinguish between those, and we do that by using subscripts. So a subscript of 1 means this sample proportion is from the first population, and subscript 2 means that this sample proportion is the sample from the second population. And we want to subtract those sample proportions minus this is the population portion from population number 1, and this is the population proportion from population number 2, we want to subtract those, but something special happens with that every single time. So it actually ends up not really being a big deal. Like this actually just goes away. Divided by the square root of, this is a new thing, it's called p bar. P bar times q bar. Now, whenever you see q, I don't know if I reference this on the next screen or not. Okay, I do. So I'm not going to write it down here, but q bar is just going to be 1 minus p bar. Just like q hat is 1 minus p hat. You know, anytime you see a q, it's always 1 minus p. So p bar times q bar divided by n1, which is the sample size of the sample from the first population, plus p bar times q bar over n2, which is the sample size of the sample from the second population. So it is a very complicated formula. It's the worst one. So I just went over this in class this past week, and the students were just like, oh my gosh, you know, what's going on here? And they were kind of scared for not just this, but like what was going to come next. But this is the worst one. So in 9.2, the formula is actually simpler than this. This is the most complicated formula really in the entire course, in my opinion. All right. Now, to calculate p bar, you take x1 plus x2 divided by n1 plus n2. Remember, x is the number of successes. So x1 is the number of successes in the first sample from the first population. x2 is the number of successes in the second sample from the second population. Of course, n1 and n2 we already talked about. So this is called the pooled sample proportion. So essentially what you're doing here is you're combining your two samples together into a single proportion calculation, right? You're taking all the successes from both samples, dividing by the entire sample size from both samples. It's like you're combining both samples together, and this is your ultimate sample size from both of them combined together. This is the number of successes from both of those samples combined together. Right. And that's the pooled proportion, p bar. And then q bar is 1 minus p bar. So we'll have to calculate that to plug it into our formula for the test statistic. So it will be quite a chore calculating the test statistic in 9.1. The other complication in this section, which I forgot, and I forgot when I went over this in class as well, because I'm like, okay, so that's it, big deal, you know, you have a more complicated test statistic, but then I forgot they also want us to calculate confidence intervals in this section. We didn't have to do that in chapter 8 because that's what we did in chapter 7. So rather than have the confidence intervals combined with the hypothesis testing in one chapter, they separated it out for those types of claims. So for claims about one sample mean or one sample proportion, sorry, I don't know why I'm saying sample. For claims about one population mean or one population proportion, they did confidence intervals in chapter 7 for that and hypothesis testing in chapter 8, and they separated those. But in chapter 9, we're going to cover both topics at the same time. So to construct a confidence interval for two population proportions, this is the formatting for that. The thing you're estimating goes in the middle. So the thing we're going to be estimating with our confidence interval is the difference in the sample proportions. So we're going to take P1 minus P2, and that's the thing we're going to estimate with our confidence interval. To estimate that, you take the sample version of that thing. So the sample version of P1 minus P2 is P1 hat minus P2 hat, right? It's the sample from population number 1, the proportion. How do I want to say that? It's just a lot of descriptors that have to go in there. It's the sample proportion from the sample of population number 1 minus the sample proportion from the sample from population number 2, right? That's the sample version of this thing that we're trying to estimate, minus a margin of error. So if you think about it in those terms, that this is just the sample version of this thing, it's just like chapter 7. It's the sample version minus the margin of error, the sample version plus the margin of error to get the lower estimate and the upper estimate for the confidence interval. But the margin of error formula is going to be different because, you know, it's a different scenario. Just like we saw in chapter 7, right? The margin of error formula was different for proportions than it was for means. it's going to be different for two proportions than it is if it's just one proportion. And so this is the formula for the margin of error. It's z sub alpha divided by 2, that's the critical value, which will actually be just the same as it was in chapter 7, but times the square root of p1 hat times q1 hat. Remember, q1 hat is going to be 1 minus p1 hat divided by n1 plus p2 hat times q2 hat divided by n2. Right, and that's how we get the sample. Sorry, I'm getting all my words. There's just so many words at this. It's just a big word soup. And when my mind goes to dig into that soup, it sometimes grabs the wrong word. So I apologize for that. So what was I trying to say? So it's going to be, so this will be your margin of error. That's what I was trying to say. This is how you'll calculate your margin of error. And then once you have the margin of error, this is how you'll set up your confidence interval. So we're going to do some examples to try to help this become a more concrete process for you, because I know just looking at the formulas, it's pretty abstract and it may be hard to kind of grasp exactly what it is that you need to do. But hopefully, once we kind of do some examples, you'll find that it's not as bad as it might look. It's complicated, but the process, you've seen it before. It's really the same process as what we did in chapter 7. This is really going to be the same process as what we did in chapter 8. So it's just the details are going to be a little different. And that's going to be a little bit more challenging, but I think you'll manage okay. You're going to manage better than you might think you will. So let's take a look at an example. 89 undergraduates were randomly assigned to 2 groups and were given a choice of keeping the money or buying gum or mints. So I think we're missing a little bit of detail here. So I apologize for that. So I think I deleted it out because it was a pretty big wall of text. And I thought, okay, I can delete out the first paragraph. It's not really necessary. But actually, it kind of helps set this up a little bit better. So what they're testing for here is I guess if we look at the claim, it kind of explains it. The claim is that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations. So the thing they were wanting to see is if they gave, in fact, I think what they end up doing here is they give some of the undergraduates a $1 bill and they give others of them 4 quarters, right? So smaller denominations, but same amount of money. And then they give them the option to either keep the money, either keep your dollar, it's either way, it's $1, right? Keep the $1 that we gave you or spend it on gum or mints, right? And they wanted to see, were the undergraduates more likely to spend their money if they had 4 quarters versus if they just had a $1 bill, right? And so that's what they're testing here. So we want to see the proportion of students who spent the money having the $1 bill versus the proportion of students who spent the money having 4 quarters. So that's going to give us 2 populations, the ones that have a $1 bill versus the ones that have 4 quarters. And then we want to get a sample, and check to see the proportion of students who are spending their money based on the denominations that they have, right? So the claim is that money in large denominations is less likely to be spent. So that means that proportion should be smaller than the proportion of students who spent their money that had smaller denominations, even though it was the same amount of money, right? We want to test this claim at the 0.05 significance level. Okay, so here's the data from this example. So we have the first column here are the students that were given $1 bills. 12 of them spent their $1 bill on gum or mints. 46 that were given a $1 bill did not. Subjects in group. Okay, I'm reading this wrong. First time I'm covering this material, so 46, so this is really this is actually making it even easier for us, honestly, but I wasn't expecting this, so I probably should just start over. So given, these are the students that were given a $1 bill, these are the students that were given 4 quarters. There were 46 students altogether that were given a $1 bill. 12 of them spent the money to buy gum or mints. There were 43 students altogether that were given 4 quarters. 27 of them spent that money to buy gum or mints, right? So this actually gives us the values for X and for N. Now this is population number 1, this is population number 2. And this is the number of successes in group number 1. So that's going to be X1. And this is the total number of students in group number 1. So that'll be N1. This is the total number of successes in group number 2. The total number of students in group number 2. Oh gosh, what am I doing? N2. I'm just losing my mind, I think. Okay. Now, so those numbers are going to be very relevant here in just a second. But to get started, the first step is just like it was in Chapter 8. State the claim, write it mathematically. And the claim is that the proportion of students in the first group who were given a $1 bill, which is the larger denomination, are less likely to spend that money on gum or mints than group number 2, the students that were given 4 quarters. So if they're less likely, that means the proportion of students in that group who are spending their money should be less than the proportion of students in group number 2 who spend their money. So they don't, again, the wording isn't very literal. We have to read the claim and then infer from that what it means mathematically. And if the first group is less likely to spend their money than the second group, then the proportion from the first group should be smaller than the proportion from the second group of students who spend their money. Right, so that is the claim. And so again, it's a little bit different than Chapter 8 because in Chapter 8, we would have one variable and we would have a number over here. But in Chapter 9, we're comparing two proportions or two means. We're going to do two means in the next section. And so in order to do that, we will have two variables. But it'll still be less than, greater than, or equal to, or less than or equal to, or greater than or equal to, one of those cases. Or maybe not equals to. So there's like 6 different things that could go there, actually. So anyways, let's move on. So setting up the hypotheses, same exact rules as we had in Chapter 8. The claim has to become one of these statements. The null has to contain equality, which means this statement, which doesn't have equality, must become the alternative hypothesis. All right. Which means the null is going to be the exact opposite, which will be greater than or equal to. All right. Then we simplify the null to just equals to. So that rule still is in effect, just like it was in Chapter 8. The alternative hypothesis doesn't change. And so we end up with this set of statements here for our hypotheses. Step 3, identify the value for alpha. Now, I'll be honest, maybe you probably could tell that I took a break. I was trying to record this video before dinner, but sometimes, I don't know if I get low blood sugar, but I was feeling like, okay, I was kind of hungry, and I just was having trouble concentrating because of that, and I feel a little bit lightheaded sometimes when I need to eat. So I had to take a break, wait for dinner to be ready, eat dinner, and now I'm back, and I'm still not very with it, it seems like. Anyways, I forgot what we had for alpha here, even though we probably already read it earlier in the video. So it's 0.05. All right, 0.05 is the value for alpha, and this is going to be a left tail test because the alternative hypothesis is a less than. So this will be a left tail test. All right. I guess it would make sense to do this over here. This is how we've done every problem in Chapter 8. We'll continue to use the same formatting in Chapter 9. And we are going to need a lot of space for this because this calculation is very tedious. It requires a lot of inputs that aren't just obvious or given to us. We have to track all this stuff down, calculate some things, and then plug it all into this crazy formula. So the formula for the test statistic, right, which is what we're doing in step 4 here, the test statistic, all right, is Z equals P1 hat minus P2 hat. And usually they put that in parentheses. Minus P1 minus P2, that's the numerator, over the square root of P bar Q bar divided by N1 plus P bar Q bar divided by N2. Now you might say, wow, this is just so complicated. Couldn't we have done something simpler than this? Turns out this is actually the simplest way this problem can be done. And there are other methods that would have different formulas for the test statistic, but they would be more complicated than this. This is actually the simplest way that you can test a claim about two proportions. The other methods are even more complex than what we're doing here. All right, so let's calculate P1 hat. That's going to be X1 divided by N1, which, again, based on the way they gave the information in the table, they made it as easy as possible as they could for us. X1 is going to be 12, and N1 is going to be 46. And you could reduce that fraction, but I'm not going to bother reducing it, and I don't want to write it as a decimal because then, again, if it doesn't work out perfectly, we'll have this run on decimal, and we don't want to have to deal with rounding issues. So just keep it as a fraction. That keeps it as an exact value. P2 hat will be X2 divided by N2, which in this case is going to be 27. I'm trying to avoid saying gonna be. I'm from Florida, and sometimes that Southern accent just kind of sneaks its way into my speech. I know there's been a few things that I say that it just comes out that way, and I can't avoid it for some reason. That was one. Gonna be is one of those things. So, anyways, not that I should be ashamed of it or anything, but just, I don't know. I kind of have grown out of that Southern accent, but sometimes it's still there in my speech. So anyways, P1 hat, P2 hat. So that gives us the values that get plugged in here. For P1 and P2, we are going to assume that the null hypothesis is true. So this is kind of like chapter 8. Assume the null hypothesis is true. So we're going to assume that P1 actually equals P2. And this is what's going to happen every time for every one of these problems in 9.1. Because no matter how these end up getting set up, once you simplify the null, it always comes down to P1 equals P2. And you're always going to assume that's true. And if that's true, then P1 minus P2 is just equal to 0, right? Because if we're assuming these are the same, that P1 is the same as P2, when I subtract them, they cancel each other out and we get 0. And so this part of the formula always just disappears. So I put it there because it's part of the formula. It technically should be there. But for every problem in 9.1, this part will always equal 0 and you can just drop it. It just goes away. Now, the last thing we need to find, because we have N1, that's here, and we have N2, which is right here. What we're still missing is P bar and Q bar. So let's find that first before we plug in N1 and N2. And so I guess let's maybe find some space up here. All right. P bar is X1 plus X2 divided by N1 plus N2. So it's not too crazy of a formula, but it is an extra step that we have to take in order to calculate the test statistic. All right. X1 is 12 plus X2, which is 27. So it's like we're combining these two samples together into a single data set, right? And if we do that, we have 12 plus 27 successes altogether out of 46 plus 43, number in our sample, right? I'm trying to think of a good way to describe that. They're people, right? But I don't know. So maybe that'd be the best way to say it. So out of 46 plus 43 total people, we have 12 plus 27 successes, which is spending the money to buy the gum or the mints, right? And so adding those together, we end up getting 39 on top divided by 89. 39 over 89. And so that would be P bar. Q bar is going to be 1 minus P bar, which will be 1 minus 39 over 89, which is going to end up being, so here's a shortcut. Because this kind of, whenever you're calculating Q, this kind of calculation occurs, right? 1 minus some fraction. It happens a lot in statistics and in probability. And so when you see that over and over and over, you do a common denominator, right? You think of this as 1 over 1. The common denominator is 89. So what you end up finding is that whatever this denominator is here, you end up getting that as your numerator over here. So the shortcut that I always use for this is I take the denominator, which is 89, minus the numerator, which is 39, and that gives me 50. So that's what's going to go on top. 89 minus 39 gives me 50. And then the common denominator will still be 89. I just keep the same denominator. And that's kind of a shortcut where I don't have to think of 1 over 1, get a common denominator. I just take, again, the way I look at it is like this. 89 minus 39 is 50 over the denominator of 89. And that's just a shortcut way of doing that computation, right? And this is Q bar, right? So now we have P bar and Q bar, so we can plug those in. So why don't we try to do that over here? I think we can have all the values on the screen at once while we do this. Let's maybe do that up here. All right, so P1 hat is this number here, 12 over 46, minus P2 hat, which is this number here, 27 over 43. All right, minus 0, because this zeroes out because we're assuming these two are equal to each other. So when I subtract them, it equals 0. Over the square root of P bar, which is this number, 39 over 89, times Q bar, which is 50 over 89, it's right here, divided by N1, which is 46, plus P bar, which is 39 over 89. Sorry, let's just redo that 3 again. 39 over 89 times Q bar, which is 50 over 89, over N2, which is 43. There's our test statistic, right? This is the value of Z. And so we'll have to plug that very carefully into our calculator. Again, use parentheses for the numerator. You can drop the 0. You don't have to type that part into your calculator. It might actually cause more problems than anything, so just drop it. But keep this in parentheses. So we're going to have parentheses 12 over 46, 12 divided by 46, minus 27 divided by 43. Close the parentheses. That ends the numerator. Divided by the square root keeps the denominator intact as one item, so we don't need parentheses in the denominator this time. But we probably do need to use parentheses here. I think that would probably be for the best. Otherwise, it might be okay, but I don't know. It gets really messy, and I'm afraid like order of operation might not work out the way it should. So to be safe, we're going to use parentheses on those. So we're going to have parentheses 39 over 89, close the parentheses on that, times parentheses 50 over 89, close the parentheses on that, divided by 46. Plus, same thing for the second fraction, parentheses 39 over 89, close the parentheses, times parentheses 50 over 89, close the parentheses on that, divided by 43, and then close the parentheses on the square root. All right, so I'm going to go ahead and write it in here so that when you see it in the notes, you'll know that's how we typed it into the calculator. Then I hit enter. Oops, I hit the wrong button. Hit enter, and I get negative, and that's okay. Test statistics can be negative. Negative 3.487. Again, my stat lab should direct you on how many decimal places to keep there. Maybe we'll go one more decimal place. So it's a 3, but the number after it is a 9, so we'll round the 3 up to a 4. Right, so there's our test statistic. So take some more time. It's a pretty complicated calculation, but not impossibly hard. So there is our test statistic. So now that we have the test statistic, which maybe I'll write again over here so we can bring it back to the rest of the hypothesis testing process. Just writing the same answer again over here. All right, there's the test statistic. So the calculation is off to the right, but we're just going to zoom back into the rest of the process. So that was step 4. Step 5 is to find the critical value or the p-value. So notice how similar this is to chapter 8. Yes, that 4th step had a lot of differences. It was a whole different formula, and it was a much more difficult formula. But other than that, the process is pretty identical to what we did in chapter 8. Again, I kind of mentioned this in the last video for 8.3. It's so similar in each section that it starts to really feel redundant. But it's good practice, right? The more often you go through the process, the better you're going to understand it, the better you'll do when you take the test. So critical value will be done exactly the same way as it was in chapter 8. It's a left tail test, so we don't want to divide the alpha by 2. We want to take the alpha as is and place all of it into the left tail since it's a left tail test. Oh, okay, there we go. All right, so this will be 0.05 right here in the left tail. We want to find, because we're back to proportions, we want to find the critical value, which will be a z-score, which means we use the normal distribution. Right. Sorry, this is bugging me too. This writing pad has really made me rethink, do I want to keep drawing these lines through my z's or through my 7s? Because I do such a horrible job of it that I really feel like maybe I should just stop doing that. Right, inverse norm, 0.05, that's the area to the left. And you don't need a degree of freedom for inverse norm. Right, and so let's plug that in. Inverse norm, 0.05, and we get negative 1.645. Just go 3 decimal places. All right, and that's it. There's one critical value this time. For p-value, you will take the test statistic. So again, 0's in the middle. So the test statistic is -3. So it's going to be over here in the left tail. -3 point, I almost put 8. Oh, come on, undo. Okay. 3.4874. Right. And we want to find the area to the left because it's a left tail test. We'll use normal CDF to do that. The lower bound is -infinity. The upper bound is -3.4874. And so that's going to give me -9999999 for -infinity. -3.4874. Close the parentheses. And I'm going to get 2.439. I'm going to stop there, times 10 to the -4. So whenever your p-value starts off with 2 point something or a number point something, you know it has to be scientific notation, because the biggest the p-value could be is 1. So sometimes I'll get students on the test where they'll say, this is my answer, 2.439. They didn't look to the end of that number to see that there was an e -4, which completely changes the nature of that number. Right? It isn't just 2.4. It's 2.4 times 10 to the -4th power. Right? The area can't just be 2.4 because the total area under the curve is 1. That's the largest number that you could possibly have for a p-value. Right? So don't just put that as your answer. Make sure you catch the rest of that number. It's scientific notation, which if we have to convert it back to an ordinary form for this number, you move the decimal to the left 4 times. You'll have 3 zeros here, then 2439. Right? And so this is the p-value. And of course, MyStatLab might ask you to round to 4, 5, 6 decimal places. I'm not sure what they would decide for you to do, but from here you could do that. You could round it however far they want you to round it. If they ask you to round it to like 3 decimal places, it just rounds to 0. If they say 4 decimal places, it's 0.0002. It's really small. It's a very small number. You don't need to double that because it wasn't a two-tailed test. You only double this area for the p-value if it's a two-tailed test. So 6, let's draw our conclusion. If we use the critical value method, and again, this is just like we were doing in chapter 8, and we did this kind of process multiple times there. Here's 0. Here's our critical value, which I like to draw as an extra long line to really show that this is our boundary. This is where we're drawing the line on where what we would consider ordinary versus extreme, right? This is where we're drawing the line on that. So I want to make sure that boundary is easy to see. -1.645. That's where I'm drawing the line. My test statistic goes further into the left tail, quite a bit, -3.4874, right? It's way over here, further into the left tail. So we reject the null hypothesis. So that's how you would use the critical value to make that initial conclusion. For the p-value method, you compare the p-value to the alpha. The p-value is 0.002439. Alpha is 0.05. The p-value is less than alpha, and so we will reject the null hypothesis. All right. So our final conclusion for this hypothesis test, we are rejecting the null hypothesis. Our claim, however, was the alternative hypothesis. So if we reject the null, we are accepting the alternative as a true statement. Our claim is the alternative hypothesis. So if we accept the alternative as a true statement, we are accepting the claim as a true statement. And so our conclusion should reflect that. There is sufficient evidence to support the claim that a student, I guess, is more likely to, or sorry, it was actually less likely, right? That a student is less likely to spend money given large denominations. Oh, why did it do that to me? It's really strange that it keeps doing that. I think maybe what's happening is it's like auto-saving, and that takes the focus away from that for some reason. So is less likely to spend money if it's given in a large denomination. Denomination, as opposed to the same amount of money in smaller denominations. All right, so maybe not the most perfect wording. And if I cared enough about it, I would look back at the problem and try to use the wording they used in the claim as closely as possible when I'm stating my conclusion. But on MyStatLab, it's going to be multiple choice, and they'll kind of do that for you. And you just want to pick the one where the first half of the sentence starts off as you see here. There is sufficient evidence to support the claim that blank. And then what they should fill in after that is the wording of the claim as it was presented in the problem. And that's really what we should strive for as well. But I think this surmises it pretty closely. On the test, again, I can be a little flexible on that, so you don't have to verbatim copy the claim into this conclusion, even though that's probably the best approach. So that is the conclusion from the hypothesis test, which took a lot of work. All right. Unfortunately, we're not done with this problem because, and this is pretty much how every problem will be in 9.1. They'll present to you a scenario. They will say, test this claim using hypothesis testing. And then they will say, test the claim by constructing an appropriate confidence interval. And so you're going to have to do two fairly lengthy things on each problem: hypothesis testing and building a confidence interval. So for this, we want to construct a 90% confidence interval estimate of the difference between the two population proportions. What does the result suggest about our claim about people spending large denominations relative to spending small denominations? So what should always happen with the confidence interval is it should be completely consistent with the conclusion from the hypothesis testing. You should not get different conclusions from these two things. So it shouldn't be the case that our hypothesis test tells us that it is true that people with larger denominations are less likely to spend than people with smaller denominations, and then have a confidence interval that says that's not the case or that it's inconclusive. Right? The confidence interval should indicate the same thing to us. All right, so let's build this confidence interval. Now, the last time we did these were in chapter 7. For chapter 9, again, the details are different, but the idea is really the same. This is the sample version of the difference between the two population proportions. This is the sample version of that. Minus a margin of error is how we will get our lower estimate. We will take the sample version of that same thing, the sample proportion from the first population minus the sample proportion from the second population, plus the margin of error to get our upper estimate. And the thing we're estimating is P1 minus P2, the difference in the population proportions. Right? And these we know. Right? It's the same values that we used in the hypothesis testing. P1 hat was, we know these, but I've forgotten them already. So let me go back and find them. P1 hat is 12 over 46. So it's going to be the same thing here. 12 over 46 minus P2 hat. I should have looked because maybe I could have remembered both of them. 27 over 43. will be 27 over 43. Right? And so that's the difference in the sample proportions minus a margin of error, which we don't know yet. So we're going to have to leave that blank for right now. P1 minus P2 in the middle. These will be the same. It'll be 12 over 46 minus 27 over 43 plus a margin of error that we don't yet know. We're going to have to calculate that. All right, oh, I just can't get these arrows right. Let me try one more time. Okay. So, margin of error. Let's do that over here, I suppose. Hopefully that's enough room there. So E, the margin of error for a confidence interval about two proportions is going to be a critical value, sub alpha divided by 2 times the square root. Now for this, we don't use P bar. We use P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N2. And this is actually an easier calculation because of that. All right. So P1 hat we already know is, and I've already forgotten it, oh, it's over there, 12 over 46 times, now Q1 hat is going to be 1 minus P1 hat. So let's use that shortcut again that I talked about earlier. This will be 1 minus 12 over 46. Now the quick way to do that calculation is to take 46 minus, so that's the denominator, minus the numerator, which is 12, and that gives me 34. 34 over the common denominator, which is 46. Right? And so that would be Q1 hat. 34 over 46 divided by N1, which is also 46. Plus, we'll do the same thing for the second population. P2 hat is 27 over 43 times Q2 hat, Q2 hat, which is going to be 1 minus P2 hat, which is 1 minus 27 over 43. And our shortcut is to take 43 minus 27, and that gives me 16 over the same denominator of 43. Right. So this will be 16 over 43 over N2, which is again 43. We're going to take the square root of that, and we also have to calculate the critical value. Now, this problem was very specific about the confidence level, but other problems, like what you're going to see in your homework, will not tell you the confidence level. They'll just say, find an appropriate confidence interval, and you will have to determine the appropriate confidence level to get the confidence interval estimate that is appropriate given the hypothesis testing that we just did. And the rule for that is that the critical value that you get here should be the same as in the hypothesis testing. So you have to choose your alpha so that the critical value comes out the same for the confidence interval as it did for the hypothesis testing. Now you might say, well, then that means alpha should just be the same number, but that's not the case, because for confidence intervals, you always divide the alpha by 2, whereas for hypothesis testing, you don't. In fact, the problem we just did, we did not divide the alpha by 2. All of the alpha went into the left tail. And so if you go back, the critical value that we want is this, without the negative sign, just the 1.645. Right? This should be the confidence, I keep saying the wrong word. This should be the critical, they both begin with C. This should be the critical value that we use for our confidence interval. Now, in order to make sure that comes out as our critical value when constructing our confidence interval, we have to choose alpha so that it covers both tails and still gives us the value of 1.645. Right? Now, the area in the left tail here was 0.05. And for the hypothesis testing, it was just a left tail test, so all of that alpha went into the left tail. But for the confidence interval, we have to also cover the right tail with the same amount of area in order to get the same critical value, which means we'll also have to have an area of 0.05 in the right tail. So this is true for confidence intervals. Right, which means the total area we have here, which is our alpha, is 0.10, which means our confidence level should equal 90%, which is what we were being asked to find. So this particular example, they were nice enough to tell us what the appropriate confidence level should be. But other problems, they won't, and you have to be able to figure it out for yourself. What confidence level do I need to choose for this confidence interval so that when I divide the alpha by 2, I'll get the same critical value that I got when I did the hypothesis testing, right? And so in this case, I would need to choose a 90% confidence level so that my alpha for the confidence interval is 0.10, so that when I divide it by 2, I will again end up with 0.05 in the left tail, so that I will get this critical value that I got in the hypothesis testing, right? That'll give me the same critical value. All right. So it's maybe the trickiest part of 9.1, really, is trying to figure that out. All right, so the critical value will be, whoops, thought I switched back to the pen, 1.645. Right? We dropped the negative sign for calculating the margin of error, but the number is the same. Right? So, and again, I'm not writing the work over here, but we just did the work on the previous screen, right? We want a 90% confidence level. That means alpha is 1 minus that, which means alpha will be 0.10. Divide that by 2. Whoops, again, I'm getting things mixed up here. Divide that by 2, and we get 0.05. That's what goes into the left tail and the right tail. And then from there, we do inverse norm to get our critical value. We'll get 1.645. We drop the negative sign, right? And so that's going to be our critical value. And so that's what I'm using over here. So now we are ready to calculate the margin of error. Well, maybe one more thing, actually, that I would like to do first, which is, and we did this in chapter 7, except here we get to do it twice. Because these denominators are all the same, we can manipulate this algebraically so that all 3 of these 46s end up in the denominator. And because it's the same number multiplied 3 times, we can write that as 46 to the 3rd power. And that just makes it easier to type into our calculator. So the 12 will stay on top, the 34 will stay on top, but these 46s all end up in the denominator multiplied together, so it's 46 to the 3rd power. We can do the same thing here. 43, 43, 43, all multiplied together is 43 to the 3rd power. On top, we'll still have 27 times 16. And I think it makes it easier to do the computation if you rewrite it in that form. All right, so we're going to have 1.645 times the square root of 12 times 34. I don't think you need parentheses in this case, but it wouldn't hurt if you wanted to put parentheses around the 12 and the 34 to indicate that's the numerator for the first fraction, and also put parentheses around the 27 and the 16. But I think order of operation will manage it just fine for us. Now, if you're not rewriting it this way, if you're keeping it like this, you would definitely, I think, want to use parentheses around those fractions. All right, so 46 to the 3rd power plus 27 times 16 divided by 43 to the 3rd power. Close the parentheses on the square root. And I end up with a margin of error of 0.16. Let's go 4 decimal places, 1614. All right, so that's my margin of error. Now that I have the margin of error, I can calculate the confidence interval estimates. So this is going to be, switch back to the pen, 0.1614 here and 0.1614, which is a pretty large margin of error. I mean, that's a 16% margin of error, but that's what it is. So now let's calculate the lower estimate here. I'm just going to type that whole thing into my calculator. 12 over 46 minus 27 over 43 minus 0.1614. And I end up with a negative value. Negative point, you might say, oh, can this be negative? I thought it was a proportion. Proportions can't be negative, but differences between proportions can. So the fact that this is negative means this estimate is asserting that P1 is smaller than P2, so that when you subtract them, the answer comes out negative. So negative, I should have put a 0 there just to make it easier to read. 0.5284. All right, so that's the lower estimate. For the upper estimate, we get 12 divided by 46 minus 27 divided by 43 plus the margin of error, which is also going to be negative. Negative 0.2056. Okay, let's try that 5 again. 5, 6. Okay. And so this 5 looks kind of funny too. Oh gosh, okay. Sorry, I messed it up. Let's try that again. Okay. 5. Okay. So, this is our confidence interval, 90% confidence interval for the difference. This is our estimate for the difference between these two population proportions. The way you draw a conclusion from the confidence interval is that if these are both negative, so if this one's negative and this one's negative, the only way, so that means whichever end of the spectrum we're on, whether we're at the low end at negative 0.528 or the high end at negative 0.2056, they're both negative. And so we are 90% confident that the difference will be negative, and it'll be somewhere between those two numbers, right? And if the difference is negative, the only way you get a negative number from subtraction is for the first number to be smaller than the second number, right? And so that's going to be our conclusion from this. Since our estimate is completely both in the negatives, so that tells me that the first number seems to be smaller than the second number. I want to say is definitely smaller, but again, it's just a 90% confidence interval. So we're 90% confident that P1 is less than P2, right? Because the only way to get the difference to come out negative, and we're 90% confident that the difference is negative, is for P1 to be less than P2, which is the claim that we just tested with the hypothesis testing, right? And so this proves the claim as well. So this confidence interval supports that claim that P1 appears to be less than P2. Now, the other definitive conclusion that we could draw is if these were both positive, that would tell us that P1 appears to be greater than P2. Right. So that would be the conclusion if these were both positive. But if it's mixed, if one is negative and the other one is positive, it's inconclusive. It's the case where we fail to, there's not sufficient evidence. There's not sufficient evidence to reject a claim or to support a claim if this is happening. Because it means it could be either one. It could be that negative means P1 would be less than P2, and that's possible because you have some negative estimates here. But because there's also some positive ones, it's possible that P1 is greater than P2. And also 0 would be contained here, because if you're going from negative values to positive values, within your estimate would be the number 0, in which case P1 actually equals P2, right? But because anything is possible in all of those, because all three of those are possibilities in our estimate, we can't draw any conclusions about it. So it's going to be the case where there's not sufficient evidence to support or reject any kind of statement in this case. So it's going to be what I just call the inconclusive case. You really can't draw a conclusion if it's mixed. If you have a negative estimate and a positive estimate, then anything is possible, so you can't draw any conclusions. All right, so that's how you'll interpret these confidence intervals as we go through a couple more of them, right? This time they were both negative, and that's fine. We drew this conclusion because of that. But here are the other possible outcomes that you need to be ready for in the other examples that you do, or the homework problems. All right, so I think I need to take a break after that one. Hopefully that made sense what I just said. So we're going to look at, I think, one or two more examples. But let me go ahead and take a break real quick, and then I'm going to resume the recording in just a minute. All right, let's take a look at this example. In a recent New York marathon, 25,221 men finished and 253 dropped out. Now be careful about that because this kind of got me in trouble. So I covered this on Thursday, but I think I skipped the first example because that didn't seem familiar to me. But I do remember covering this one in class, and I misinterpreted these numbers also. I made the same mistake in the first example, misinterpreting the numbers I was given. And I did the same thing on this example. So think about what that means. We'll talk about it here when it becomes relevant. Also, 12,883 women finished, and 163 dropped out. We want to use a 0.01 significance level to test the claim that the rate of those who finish is the same, for men and women. All right, so test the claim using a hypothesis test. That's part A. Part B, test the claim by constructing an appropriate confidence interval. So here they're not telling us what confidence level to use. We have to determine what would be appropriate in this case, unlike the last one where we were kind of told what to do. All right, so we'll start with the first step of hypothesis. So we're going to do part A first, hypothesis testing. Step 1, state the claim in a mathematical form. Here we're being told the claim is that the rate, which is the proportion, of those who finish is the same, which means they're equal to each other. And so the claim here is that the proportion of men who finish the race is equal to the proportion of women who finish the race. All right, so that is the claim. And so just based on the order that the data was given to us in, we're going to let 1 represent the population of men who raced in the marathon, and 2 will represent the population of women who raced in the marathon. All right. Now we'll set up the null and the alternative hypotheses. All right, and so we're going to take P1 equals P2. Again, this statement has to become one of these. The null has to contain equality. Well, this has equality, so that will have to be the null. So P1 equals P2. The alternative will be the opposite of that. The opposite of equals to is not equals to. And this time we don't need to simplify it because it's already in its simplified form. The null hypothesis is already just equals to, which is what we want for the final statement. All right. 3, identify the value for alpha, which is 0.01. And whether it's a left tail, right tail, or two tail test, not equals to means this will be a two tail test. All right. Now the worst part of the whole problem, the test statistic, right? So Z equals P1 hat minus P2 hat. Even though this is going to equal 0, I still like to write it in there, P1 minus P2, over the square root of P bar times Q bar over N1 plus P bar times Q bar over N2. All right, it's a tough formula, but let's just, and again, you're probably feeling the same way I am right now, which is, I just don't feel like, there's so many things to do, you just kind of don't feel like even starting on it, but you just got to take it one thing at a time. Eventually, all the pieces fall into place and it works out just fine, and it's not as bad as it might seem. All right, now P1 hat, this one is kind of tricky though. Remember, P1 hat is equal to X1 divided by N1. Now, we're talking about the proportion of men and women who finish the race. So that is what we are going to consider a success. And why my computer does this. It drives me crazy. Honestly, it's a conspiracy theory, but I have McAfee on this computer, which, you get free for like 30 days. I haven't deleted it off my computer, but I've heard some questionable things about the McAfee antivirus software. So, as far as it being like kind of like a virus in and of itself, and I wonder, because sometimes I'll get these pop-ups on my screen that interrupt what I'm doing, and I'm wondering, is that what's interrupting me periodically when I'm doing other things? Like it just locks out for 20 seconds. Like why would my computer do that? So I don't know. My conspiracy theory is it's McAfee. I think that's what's causing it. So anyways, I don't remember the mistake I made now, because now that I think about it, like, how could I have made this mistake? I don't know. 25,200. I think maybe I was going to subtract these. I'm like, well, this is the number of people that raced minus this many that dropped out. I think that was the mistake I was making. But this isn't the total number of men in the race. This is the total number of men who finished the race, which means this is my number of successes. So I wasn't given N, right? I was given X for the men who participated in the race, but not N. I have to calculate N in this case, right? So the number of successes is 25,221. That's how many people finished the race. Out of how many men actually entered the race, it was this 25,221 plus this, right? The number that dropped out. You want to add those together. And so we have 25,221 plus 253. And so we have 25,000, and this problem's just made all the worse because these numbers are just such big numbers. 25,474. Right? That's the total number of men in the race. So we have to take these two numbers and add them together to get in. All right. And so this is P1 hat, which is an awful fraction, but it's probably even worse as a decimal. I'm just going to leave it as a fraction. Do the same thing for the proportion of women. P2 hat will be x2 divided by n2. It's x2 that's given to us. Sorry, I just can't let that go. That 2 is kind of bugging me. All right. x2 is given to us here. That's the number of women who finished the race. This is x2. So it's going to be 12,883 over the total number of women who entered the race, which we can find by adding the number who finished to the number that dropped out. So it's going to be 12,883 plus 163, which gives me 1346. And that isn't quite right what I said. 13,046 would be a better way to say that. All right. And so that gives me the value of N2. I should have put N1 up here for that. Okay, so there's P1 hat and there's P2 hat. So I'm ready for this numerator, but I also need to find P bar, right? So P bar is going to be X1 plus X2 divided by N1 plus N2. X1, as we already identified up here, was 25,221. Plus x2, which is the 12,883, divided by, I was a little bit too close to those numbers, divided by n1, which is the 25,474, plus n2, which is the 1346. And again, I'm not going to plug that into my calculator to get a decimal. I'm going to keep it as a fraction because that keeps it as an exact value, and that way I don't run into getting into the issue of getting a wrong answer because of how I rounded my value for P1 hat or for P bar, right? So we're going to have 25,221 plus 12,883, which gives me a grand total of 38,104 people that finished the race. That's men and women combined, out of 25,474 plus 13,046, out of a grand total of 38,520 people who entered the race, men and women combined. Right. Let's try that 0 one more time. Ugh, okay. Now one more time. Okay, let's get this right. Okay. And so that's the value of P bar. Now to calculate Q bar, it's going to be 1 minus that, 1 minus P bar. And so let's scoot over here so we can see what we're doing. So that's going to be 1 minus 38104 over 38520. Again, let's use our shortcut that I introduced earlier in the video. Take the denominator, which is 38520, minus the numerator, which is 38104. And that gives me 416 over the denominator of 38520. And that's going to be the value for Q bar. So now I think we have everything that we need. So I need room to actually plug it into the formula. And I would like to keep all the numbers on the screen at the same time, but everything's all over the place. So I'm just going to try to remember these numbers the best I can. So P1 hat was 25,221 over 25,474 minus P2 hat, which is 12,883 over 13,046. I forgot to mention this, but this is just going to equal 0, so we don't need to, I guess I've been writing it in here, but minus 0, all right, I forgot to mention that over here. So assume this is true. So it's the same as the last problem. If you assume P1 actually equals P2, this means that P1 minus P2 is going to equal 0, right? Because if they're the same, which is what we're assuming, then when you subtract them, you'll get 0. And again, my 0, it's driving me crazy. 0. Okay, there we go. All right. So that'll be 0. Okay, so back to this. P bar was, okay, I can scroll up to see that a little bit better. So right there. All right, so we're going to have square root. We're going to need a lot of space for this. P bar, which is 38104 over 38520. See, now it's going to mess with, never mind. I'm just not going to talk. I'm not going to say anything. Okay. Times Q bar, which is 416 over, again, 38520. That's Q bar. That whole thing over N1, which was 25474. That's just the first fraction. That's just this part. Plus, same thing again, P bar, which is 38104 over 38520 times Q bar, which is 416 over 385. Why did I put 5 twice? Okay. That's why, because I should have put an 8 first before the 5. 38520 over N2, which is 13,046. Okay. There is our test statistic with all the numbers plugged in. Now, and I'm sorry, it kind of got messy here, but the square root applies to the whole thing, and it should go all the way to the outside there, but I'm not going to rewrite it at this point. Let's just plug it into our calculator, and we're going to get, remember, use parentheses for the numerator, parentheses 25221 minus 12883, close the parentheses, drop the 0. You don't need it. It's just going to get in the way. It's just going to cause trouble. It's just 0, so it just goes away. Divided by the square root. Again, I would recommend putting these in parentheses just to make sure the order of operation works out exactly the right way. So we'll have parentheses. So when I do my square root symbol, it automatically puts a parentheses for what goes in the square root. But I'm going to put yet another opening parentheses for that first fraction. 38104 divided by 38520. Close the parentheses on that fraction, times new parentheses, 416 divided by 38520. Close the parentheses on that. Divided by 25474. That's the first fraction. Plus, start over again, parentheses, 38104 over 38520. Close the parentheses. Times new parentheses, 416 divided by 38520. Close the parentheses. Divide that by 13,046. And then close the parentheses on the square root. And hit enter. And oh man, something must have went wrong. Okay, so the number I got in my calculator, I should show you. It's kind of humorous. It's a really big number. I don't know if you can see it. It's hard to tell on my screen if it's showing up very well. But it's something like, let's see, what is it? 11 million and something. Which remember, so this is why you got to, because like some students will be like, oh, okay, that's the z-score, 11 million, 87,000, which is a ridiculous number for a z-score, right? Even 23, remember, we saw that in a previous video, is ridiculous for a z-score. That's a really large number for a z-score. 11 million just should never, ever happen. Over 100, 78 should never happen, and we saw that one once, and that was ultra extreme. 11 million is just absurd. It just can't be right. So I look at my calculation, and I forgot to put the denominators on my fractions on the top. So I put 25221, but I forgot to put over 25474. And so I need to go back. I have to redo this whole thing, which is unfortunate. So I'm going to pause the video so you don't have to sit there and watch me type all this into my calculator again. And then I'll resume it with the answer. All right. And so I end up getting this time don't know why that didn't work. I'm going to go 4 decimal places. 3029 if I round to the 4th decimal place. That's a much more reasonable value for the test statistic, right? 11 million just didn't even make sense. So 2.3, that's what we should have gotten the first time. All right. Now that we have that, let's just get all that work out of the way. I don't even want to look at it anymore. All right. Next step, critical value. And we're just back on track to what we already learned how to do in Chapter 8. Everything from this point on is the same as what we were doing before. Critical value, we take, in this case, we have to take alpha and divide it by 2 because it's a two-tailed test, right? So take alpha, divide it by 2. That's going to be 0.01 divided by 2, which is going to give me 0.005. I'm dividing it by 2 because for a two-tailed test, that alpha has to cover both tails. So we put half of it into the left tail and the other half into the right tail. So we're going to have 0.005 in the left tail, 0.005 in the right tail, which means there's actually two critical values here. But we can find both of them at once by just doing inverse norm. Area to the left in this case is 0.005. This is going to give me the critical value that's in the left tail. Inverse norm 0.005, which is going to be negative 2.576. If that number looks familiar, we've seen it multiple times before, because with the normal distribution, if your alpha is the same, your critical value is the same. Or if the area is the same, you'll get the same critical value. For the t-distribution, it keeps changing depending on the sample size, right? But for the normal distribution, 0.005 always gives us this critical value, and we've seen this one a few times. That's the critical value in the left tail over here, but there's also a corresponding critical value in the right tail. Because of the symmetry, it's going to be the same number but positive. And so we'll get positive 2.576 as the critical value in the right tail. So there are our two critical values. Now for p-value, we take test statistic, which is this. Sorry, I don't know why I did such a bad job underlining it. And we find the area that corresponds to that critical value. Zero's in the middle. This is positive, so it'll be closer to the right tail, 2.3029. And when it's a two-tail test, you find the area to the closest tail. So this test statistic is closer to the right tail, so I find the area to the right by doing normal CDF. The lower bound there is 2.3029. I'll scroll over a little bit since I'm out of room here. The upper bound is infinity, and that's it, right? There's no degree of freedom. And so that's going to give me normal CDF 2.3029, comma, 9, a bunch of 9s. And I get 0.0106. However, there's a reason why I left kind of a gap there. Whenever it's a two-tailed test, you have to multiply this area by 2 to get the p-value. The reason we're doing that is because we had to divide the alpha by 2, which we saw for the critical value is what we had to do. But for the p-value method of comparison, we don't want to change alpha. We want to leave alpha as 0.01. But really, it needs to be divided by 2. But in exchange, instead of dividing the alpha by 2, we decide just to double this area in order to compare it to alpha. Right? So really the comparison here should be this number to the alpha divided by 2. That's the two numbers we should compare. But we will draw the same conclusion if we don't divide the alpha by 2, but instead just double what this area is. And we'll draw the same conclusion either way. So let's double that. So multiply by 2, and we get 0.0213. Now, again, if you just go by this number here, it would be 12, but I kept the exact values in my calculator. So that way, so I just did times 2 to my previous answer. So it has all the decimal places, and it actually does make a difference here to the 4th decimal place, keeping those extra digits. So this would be the more accurate answer here. And that's going to be my p-value. All right, to 4 decimal places anyways. All right, now we want to draw our initial conclusion. Do we reject or do we fail to reject the null hypothesis? All right, so this is step 6. It's just, I'm sorry, it just bugs me that why did I undo so much? Okay, step 6. So if we use the critical value method, we have 2 critical values here. So negative 2.576 and positive 2.576. As long as the test statistic stays between these two numbers, we will fail to reject the null hypothesis. Right? So if it stays in between these two numbers, we fail to reject. However, if the test statistic becomes more extreme, if it goes further into the left tail or into the right tail, we will reject the null hypothesis. So where is our test statistic? I don't remember what it was. It was kind of like on the fence there. So it's 2.3, which is really close but does not cross the line, right? So 2.3 is going to be about right here. 2.30, what was it again? 2.3029. That's our test statistic. It stays between the two critical values, so we will fail to reject the null hypothesis in this case. If we use the p-value method to test it, the p-value was 0.02. It looks like a 1 from here, but I thought it was a 2. Oh, it's just the decimal place. Okay. 0.0213. Alpha was 0.01. The p-value is greater than alpha, which means we fail to reject the null hypothesis. So same conclusion from that. And so our final conclusion about the claim is as follows. So let's go ahead and just type it out here. All right, so let me get my keyboard and let's put it right here. There is, now we have to decide, is it sufficient or not sufficient? Well, if we're failing to reject, whether we're supporting the claim or rejecting the claim, failing to reject the null hypothesis means we're not going to do either of those. We're not going to either be able to support or reject anything here because we're failing to reject the null hypothesis. So we're going to have to say there is not sufficient evidence. But then we have to decide, is it not sufficient evidence to support the claim, or is it not sufficient evidence to reject the claim? So remember, the null hypothesis is the claim. Our claim became the null hypothesis because it had equality in it. Right? So I'll show you in just a second that's what happened. But our claim is the null hypothesis. So by failing to reject the null, we are failing to reject the claim itself. So there is not sufficient evidence to warrant, this is how they like to word it, rejection of the claim that the proportion of people who finish the race is the same for men and women. I don't know. Hopefully that captures the meaning of the claim. Okay. Again, that's not the exact wording that was used in the problem, but I think it paraphrases it well enough. Okay, so that'd be our final conclusion in this case. Right. There wasn't enough evidence to warrant rejection of that claim. Now, if you were hoping to be able to prove it was true, that men and women finish at the same rate, we talked about this in a previous video, you can never prove a null hypothesis true. You can only ever show that it's false. So if you want to prove something like that, you can't have equality in your claim. So when your claim is that the proportions are equal to each other, that automatically sets it up so that either you're going to be able to show it's false or you're going to be unable to show that it's false. That's the only two conclusions you're going to be able to draw about that claim, because that claim becomes the null hypothesis. And that's all we are going to be able to say about the null hypothesis. That being said, if you test this over multiple years, so if we kept checking the data from the New York Marathon, and for 10 years running, we are unable to prove that claim false, that's pretty good evidence that it's likely true, right? Because you've tried over and over and over to prove it was false, that the proportion of men and women are not equal, right? Because that's the only possible conclusion that we could draw based on the claim that's being stated. And over again, we're unable to prove that it's false. And so that makes it a pretty strong claim, because it seems to be, impervious to attack, right? Every time you get a sample, you're attacking that claim. And every time the claim is rebuffing that attack and saying, sorry, you don't have enough evidence to prove that I'm false. And so it seems like it could likely be a true statement if we were unable to reject it multiple times. So from this one instance, it's hard to really say. But if we checked 10 years worth of data, and in each year we ran this hypothesis test, and every single time we're unable to prove that claim false, that really kind of makes it, that makes a strong case that it's very likely a true statement. All right. Okay. That being said, we still had a part B, right? So that was a lot of work to get through that problem, and we're only I'd say more than halfway done. I think most of the work is part A, but there's a little bit more work to do in part B, which was, and I said I was going to show you this, by the way. So the claim became the null hypothesis. So whatever we say about the null, we're saying about the claim. We want to construct an appropriate confidence interval. Now this time we have to decide what confidence level to use. My advice is, now here's the thing. You might know by now, and I haven't really let on this summer about this, but a lot of these hypothesis testing can be done on the TI-84. So it does everything for you, and it'll tell you a lot of the stuff that you need to know to get the answer right on MyStatLab. It'll tell you whether you, I don't know if it tells you the conclusion, but it will tell you the p-value, it'll tell you the critical value, it'll tell you the test statistic. It gives you those numbers, and then you can use those to decide whether you should reject or fail to reject, right? And then draw your conclusion based on that. So it doesn't tell you what the conclusion is, but it gives you the numbers to do that. So you don't have to calculate them by hand. Same thing with the confidence interval. So there's actually a function on the TI-84 for constructing a confidence interval for two proportions. It's called something like 2prop z int or something like that. So two proportions, normal distribution, which is what z is referring to, int for interval, right? Confidence interval. But it doesn't tell you the confidence level to use here. So you would have to determine that in order to use your calculator to construct the confidence interval for you. So you're gonna have to figure that out, right? What I think is easier to do is to do the calculation by hand, and I'll show you how you can work backwards from that to figure out what the confidence level is for this confidence interval. So what we're gonna do for part B, oh gosh, what is going on there? That was supposed to be a B, okay, is we're gonna construct a confidence interval using this formula, P1 hat minus P2 hat minus the margin of error. That's our lower estimate. I don't know why I put parentheses there. The thing we're estimating goes in the middle, and then our upper estimate will be P1 hat minus P2 hat plus the margin of error, right? Now we know the sample proportions. We had to have those for part A, and we'll just use them again here for part B. So P1 hat was 25221 over 25474. And P2 hat, just can't get these arrows right. Oh gosh, that was even worse. Okay, was 12883 over 13,046. And we want to subtract those two. So I'm sorry that minus sign is gonna kind of blend in with those fractions. And then we want to subtract a margin of error from that, which we're going to have to calculate. We don't know what that is yet. We'll do the same thing here. We're going to have 25221 over 25474 minus 12883 over 1346. Right? I should put these in parentheses, I guess, just to make it easier to read. Plus the margin of error, which I'm going to try to squeeze in right there, I guess. Right, and the thing I'm estimating goes in the middle, which once I get these numbers, I will recalculate. So this is the lower estimate, this is the upper estimate. We'll get the numbers here, and then we'll bring that P1 minus P2 down once we get those numbers. But before I can do that, I have to find the margin of error. So let's scroll down a little ways further down here to do that. So I think this should be enough room to finish out the confidence interval. So E, remember, is Z sub alpha divided by 2 times the square root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. All right, now here's where I've made no decision about what the confidence level is for this particular confidence interval that we're making. I haven't asserted any confidence level yet. I wait until this moment to make that decision. So what I know about making this an appropriate confidence interval is that this critical value should be the same critical value that we got in the hypothesis testing. So it should be this number here, right? The positive one, right? If there's two of them, you want the positive one. And if there's only one and it's negative, you drop the negative sign for use in the margin of error formula. So whatever critical value you found in the hypothesis testing in part A, you want to use that same critical value here in part B for the confidence interval. So that's going to be my critical value, 2.576 times the square root of all this stuff here. Now to get that critical value, the way we calculated it was using an area of 0.005, which we have to, now it's going to sound weird to say this, but whatever that area was to give you that critical value, you have to apply it to both tails of the normal distribution, which was already the case for part A. Because it was a two-tail test, we did have this as our area in both tails. But even if we didn't, for the confidence interval, whatever area is giving you this critical value in part A, you have to make sure that area is matched in the other tail. And then you want to combine those areas together to get your alpha for part B. So our alpha for part B, we combine these areas together, we're back to 0.01 as our value for alpha, which means my confidence level for part B is going to be 99%, right? Because the alpha is 0.01, means we have a confidence level of 99%. All right, so that's how you figure out the confidence level. You get to the part where you calculate the margin of error, go back to part A, find that critical value, and use that as the critical value for the margin of error. Then look at the area that gave you that critical value, make sure to match it in the other tail if it's not already matched, and then add those areas together to get your alpha for the confidence interval. 1 minus that gives you your confidence level, right? 1 minus 0.01 gives me 0.99. It's 99% confidence level. All right. That's the way that I approach this. And I just don't use my calculator to get the confidence interval, right? Okay, so P1 hat. We already know this. These numbers are so big. I'm having a fatigue here from dealing with these numbers. 25221 over 25474, right? That is the value for P1 hat. Now for Q1 hat, we haven't calculated that yet, so I need some more space to do that calculation. Q1 hat is 1 minus P1 hat, which will be 1 minus the 25221 over 25474. Again, we've talked about the shortcut, which is almost indispensable in this section because that calculation comes up so often with such horrible fractions. This shortcut's a big time saver. 25474, that's the denominator, minus the numerator, which is 25221. That gives me 253, which you should recognize. That's the number of men who did not finish the race. And that's what Q is representing. P is the proportion of successes. Q is the proportion of failures. I mean, I shouldn't say fails. That's just internet lingo there, isn't it? So it's the proportion of failures, right? Which is the number of people that didn't finish the race, which is 253 for men, right? Out of the 25,747 men who entered the race, right? So that's Q1 hat. And so that's what I'm going to put here. 253 over 25474 over N1, which is 25474. Right, that's just the first fraction. I did not leave myself enough room here. So plus, we'll do the same thing for P2 hat. It's going to be 12883. I'm going to have to write really small here, over 1346. And instead of me writing it out on paper over here, let's just, I mean, again, the pattern's pretty obvious. And also, we can see this number is the number of people who did not finish the race. For men, we do the same thing for women. How many women didn't finish the race? It's given in the problem. But we can also do the shortcut 1346, that's the denominator, minus the numerator, which is 12883. And that gives me 163. There was 163 women that didn't finish the race out of 13,046 women who entered the race altogether, divided by N2, which is 13,046. And that's going to be my margin of error. Again, I like to rewrite this where these three numbers are together, raised to the third power. Just makes it easier to type into my calculator. So here's what I'm typing into my calculator. Whoops, that's supposed to be an equal sign. Equals 2.576 over the square root of, this will be 25474 to the third power. On top, we'll still have the 25221 times the 253. Plus, we'll do the same thing here. This will be 13,000, supposed to be a 3, looks like a 5. 13,046 to the third power. And on top we'll have 12,883 times 163. All right. And so that's what I'll type into my calculator. 2.576 times the square root of 25221 times 253 divided by 25,474 to the third power plus 12,883 times 163 divided by 13,046. Almost made a mistake there. 13,046 raised to the third power. Close the parentheses on the square root, and I get quite a small margin of error here. We get 0.00029. Oh, it's messing up again. 2973. I don't know. 4 significant digits, I guess, will be fine. So that's the margin of error. Now I can calculate the confidence interval. So I go back up here with that margin of error. And so that's what I'm going to put here. It's going to be 0.002973. And same thing here, 0.002973. All right. And so this is what I type into my calculator to get my lower estimate. So we're going to have 25221 over 25474 minus 12,883 divided by 1346 minus the margin of error, 0.002973. And I get as my lower estimate negative 4.104 times 10 to the negative 4. For my upper estimate, we will have 25221 divided by 25474 minus 12,883 divided by 13,046 plus the margin of error, 0.002973. And we end up getting positive, right? This time it's going to be 0.00553. Or if we go 4 significant digits. Now this is actually going to be negative 0.000. You get 3 zeros, 4104. All right. And then this will stay the same. I should have done that over here too. Sorry, I should be consistent. Oh, it's not going to work. Erase. Let's erase this part here. Put a 0 in front of this also. So 0 point that, and it's negative. 0.005536. Right? So this would be my confidence interval. It's my 99% confidence interval estimate, which is the appropriate level to use so that it corresponds to the hypothesis test that we did in part A. And as I mentioned on the previous problem, this is the inconclusive case because one side is negative, the other side is positive, so anything is possible. If this difference happens to be negative on the negative side, then P1 is actually less than P2. If it happens to be on the positive side, then P1 is greater than P2, and also 0 is within this estimate. So if it happens to equal 0, P1 is actually equal to P2. And all three of those are possible, right? And so we're 99% confident it could be any of those three cases, and so we can't draw any conclusions. We don't know if P1's bigger or smaller or equal to P2 because this estimate allows for all three possibilities, right? So this is the inconclusive case, which is consistent with the conclusion that we drew in part A, right? There's not sufficient evidence to warrant rejection of the claim. All right, we have one more example here. Now this video is already an hour and 30 minutes long. I might cut out a little bit of it because there was a couple spots that I wanted to go back and remove some gaffes and whatnot. So what I'm going to do with this last problem is I'm going to pause my recording and work out both parts A and B first, and then I will resume it and just kind of walk you through it. I think it's a great opportunity for you to try the problem yourself to see if you can follow through this hypothesis testing process on your own and also follow through on the confidence interval process on your own. And then you can check your answers with my answers and see how you did. So I'll go ahead and read the problem to you, and then I'm going to pause my recording. You should pause the video. We'll both work out the problem, and then you resume playing it, I'll resume recording, and then we can check our answers together. So, in a random sample of males, it was found that 23 write with their left hands and 217 do not, which I assume means they write with their right hand. In a random sample of females, it was found that 65 write with their left hands and 455 do not. We want to use, now you might say, okay, so if they're not writing with their left hand, they must write with their right hand. It's possible some people might not even know how to write. And again, if you want it to be a binomial situation, right, success and failure, you have to make it so there's only two options. And if we said left hand, right hand, what if somebody they picked couldn't write with either hand because they didn't know how to write at all, like they never learned how? Then that's a third option. So that's why it's kind of worded in this funny way. Either they're writing with their left hands or they're not. That gives you two options, right? So let me resume. In a random sample of females, it was found that 65 write with their left hands and 455 do not. We want to use a 0.05 significance level to test the claim that the rate of left-handedness among males is less than among females. So let's test that claim using the hypothesis testing process, and then also test the claim by constructing an appropriate confidence interval. All right, so good luck. Okay, so here are the answers that I came up with. So a couple things to note. What we're given in the problem is x1. That's the number of people who write with their left hands. But we're not given the value of n. We have to calculate that by adding the people who write with their left hands to the people that don't to get the total number of people in the study. So N1 actually is 23 plus 217, which is 240. Right, so N1 is 240. I didn't write it on the screen here, but you'll see it on the next screen. For the females, we have 65 who write with their left hand. That's X2. But then to find N2, we have to add 65 to 455, and we get 520. I guess you can see the numbers down here. So for P bar, it's going to be X1 plus X2 divided by N1 plus N2. So you see these are our two values of N. Those are our two samples as for the men and women. Right? And so P bar ends up being 88 over 760. We use our shortcut to find Q bar. You take 760 minus 88. That becomes the numerator for Q bar. The denominator stays the same. And we're going to need that on the next screen. All right, so first we do the hypothesis testing. Oh, sorry, this is the end of it. Let's go back to the beginning. The claim is that the proportion of men who are left-handed is less than the proportion of women. Right, so that's the claim. That gives us these hypotheses initially, but then we simplify the null hypothesis to just equals 2. And so this becomes the null and the alternative hypothesis that we work with. Alpha was 0.05, which actually I started to doubt myself on that, but no, that is what it says. Okay. And it's a left tail test because the alternative hypothesis is a less than. Then we do the crazy calculation of the test statistic in this case. So there's the formula again. You plug in P hat, P1 hat, P2 hat. Again, P1 minus P2 ends up being 0 when you assume that the null hypothesis is true. I didn't write it down, but we're assuming this is true, that P1 actually equals P2. For the sake of argument, that means this would be 0 in that case. So we get 0 again, like we did on every problem before this one. P bar, as we already mentioned, was 88 over 760. Q bar divided by N1. P bar times Q bar divided by N2. Put that into your calculator. I ended up getting negative 1.1681. So that's the value that I come up with for the test statistic. This one's kind of a pretty ordinary z-score, so I'm guessing we're going to fail to reject, but we want to make it official, so we want to compare that to either the critical value or convert this to an area, which is called a p-value, to compare to alpha. But either way you do the comparison, you do fail to reject the null hypothesis. All right, so the critical value in this case, alpha is 0.05. It's a left tail test, so we put all of it in the left tail. Inverse norm on that, we get negative 1.645. That's the cutoff value. That's the cutoff line. Anything more extreme than that would cause us to reject the null hypothesis. But this test statistic is not more extreme than that. It's less extreme. It's over here. So we fail to reject. And again, I'm using obscure language. I don't know why. I think I started with that habit early on when I was teaching this course for the first few times, and it's a hard habit to break. So any test statistic more extreme than this, we would reject the null hypothesis, but the test statistic is not as extreme. If you want to use the p-value to draw that conclusion, you take the test statistic, which is this value here. It's a left tail test, so find the area to the left. We use normal CDF to do that. We end up getting 0.1214. You do not need to double this because it's not a two-tail test. So that is our p-value. It's greater than alpha, which leads us to that conclusion that we should fail to reject the null hypothesis. So our final conclusion then is that there is not sufficient evidence to support the claim that the rate of left-handedness in males is less than the rate of left-handedness in females, right? We fail to support the claim this time because the claim is the alternative hypothesis, not the null hypothesis. We are failing to reject the null, which means we are failing to accept the alternative. The claim is the alternative. So whatever conclusions I draw about the alternative hypothesis, I'm drawing about the claim itself. I'm failing to support the alternative hypothesis, so I fail to support the claim itself. And that's why we use that language there. All right, so that's the conclusion for the hypothesis testing. For the confidence interval, I'm sorry, this is a scary mess to look at. Let's start from the beginning. This is the formula that we want to use. We already knew P1 hat and P2 hat, so I plugged those in right away. But I didn't know E, so this was blank initially. Maybe I should also kind of fill this in a little bit right here. Sorry about that. All right. And then, same thing for the upper estimate, P1 hat minus P2 hat, plus the margin of error, which again, we didn't initially know. So I left that blank. Then I went to go calculate the margin of error. I have not yet decided what the confidence level should be. I'm just going to go to my margin of error calculation. And for the critical value, I want to use the same critical value from part A, which was 1.645. Now in part A, it was negative because it was a left tail test. But for the margin of error formula, you always drop the negative sign. So we want to use positive 1.645 as our critical value. Now, in order to get that as our critical value in part B, we need to have an area of 0.05 in both tails, right? So the area of 0.05 is what gives us the z-score of 1.645. In part A, that area was just the left tail, but we have to match that area in the right tail as well for the confidence interval. So we'll have to have a matching area of 0.05 in the right tail, which gives us a total area in both tails of 0.10, which means our confidence level will be a 90% confidence level. So that is the confidence, that's the appropriate confidence level to use relative to the hypothesis test that we did in part A. So that's our critical value. P1 hat we already knew. Q1 hat we find by taking 1 minus P1 hat. And again, I use the shortcut. 240 minus 23 gives me the 217, which is a number that's actually provided in the problem itself. These are the number of people that do not write with their left hand. It's the number of failures, right? Over the sample size, which is 240. Do the same thing for females, right? 65%, not 65%, sorry. 65 write with their left hand. 455 do not. So Q1, sorry, I said Q1. Q2 hat becomes 455 over 520. Maybe if I just slowed down and think for a second before I speak, I might not make so many verbal mistakes like that. I apologize. All right. So that's how we get P1 hat, Q1 hat, P2 hat, Q2 hat. Or you could use the shortcut, 520 minus 65, that gives you the 455. That's what I did. I didn't actually look back at the problem. Over N1 in this case, over N2 in this case. And what's nice is that these three numbers are the same, so we can reorganize that as 240 to the third power and 520 to the third power. I type that into my calculator. I get this margin of error. It's roughly 4%, 4% margin of error. And so I go back up here and plug that in for E. Plug this into my calculator. I get negative 0.06849. Plug this into my calculator and I get positive 0.01015. So again, I'm going 4 significant digits in both cases. Again, just like the last example, our estimate ranges from negative differences to positive differences, which means this is the inconclusive case because if the difference is in fact negative, which is a possibility, P1 would be less than P2 for that to be negative. If the difference is positive, which is also a possibility according to our estimate, then P1 would actually be bigger than P2 for that difference to be positive. And 0 is also a possibility here, which means P1 could also possibly equal P2. And there's no way to know which one of those is the true one because our estimate makes all three possibilities possible. Oh, that's so redundant. That's such a horrible way to say it, but hopefully it makes sense, right? So our estimate runs from negative to positive values. So all three conclusions are possible with this estimate, which means we cannot make a decision on which one is true, right? So it's the inconclusive case. It's possible P1 is less than P2, but our estimate also says it's possible P1 is greater than P2 or that P1 is equal to P2. So no conclusion can be drawn about P1 and P2, which again is consistent with the conclusion that we had from the hypothesis testing. So this was a long enough video. I'm sorry I didn't expect it to take 2 hours. That's a lot longer than I thought it would take. So I apologize for that. I will see you in the next video for section 9.2.